Hi guys, this is Christian Horner, and today we're going to talk a little bit about Intro to Forces, or better said, may the Ma be with you. So if you're a Star Wars fan, you'll understand that, and if you're not, you will hear shortly. Hopefully, that will help you a little bit. Just want to make sure everybody can hear me. So if you can hear me down in the bottom corner, you'll see, I think it's over here. You'll see a little chat button there and it says, say something nice. So just let me know if you can hear me. I've got one person so far who says yes, and we've got a bunch now. Awesome. That's what we want. Here we go. Remember, this is brought to you by Think Fiveable. So these are a series of different videos that you can watch. You come on live and you can go through these with me. And if you have a piece of paper and a pencil, that will help too, because you can go through, and if you need to write anything down, you sure can do that also. Think Fiveable is a platform where we help any student in any AP course. You can go on and take a look at thinkfiveable.me. But you can also, if you like anything, go through and tweet it, use Instagram, or go to YouTube, watch some videos, and leave some comments. We'd really appreciate that. There's some other streams this week. So on the 1st, which is on Tuesday, Jenny Kostka is going to go through at 8 o'clock the gravitational field. On the 2nd at 7 p.m., Peter Apps is going to talk about free body diagrams. So if you need help in those, that'd be a great one to go to. And then finally on 10/3 at 9 p.m., Casey Lee, who's an awesome student, is going to go through some problem solving practice and some Q&A. I also see that we do have a question tonight. Somebody wants to know about tug of war and is asking about tension in the line. So we will do that the very last thing. Here we go. Let's go ahead and talk about what is in this stream. So in this stream, we're going to talk about several things. First of those is, what is force? Other than something that you've heard about and maybe you know it's a push or a pull. You've also know that it's on Star Wars, but you're not really sure about anything else. This little program will help you tremendously, I hope. We'll talk about the different types of forces. We're going to talk about two things that you should always know about forces. Then we're going to look at Newton's 3 laws, first, second, and third law. I know that's really difficult. And then finally, we're going to end up doing 5 multiple choice questions, and I will take you through and kind of help you with those also. So here we go. So what in the world is a force? We know that it is a physical quantity. And there's a couple of different types of forces. So we have to be careful when we say that they're a physical quantity, because they can be one of two types. They either can be a contact force. So for example, let's say that I go to Meijer, or I go to Kroger, or I go to Walmart, just in case none of those places sounds familiar, and I grab a shopping cart just like this, and it's got wheels on it, a little basket underneath, and I push it. This is a contact force because I am actually physically making contact. So this is actually making contact a little bit. The other thing is we could also have a non-contact force. So non-contact force, C-O-N-T-A-C-T. So we also have a non-contact force. And non-contact forces include, for example, I am floating above the Earth, so maybe I'm in the space station, but there's still a force pulling me down, and that is the force due to gravity. In fact, we say this is a non-contact force even though we're on the Earth, and it's because gravity really is coming from the very, very, very center of the core of the Earth. You could think of it more that way than you do anything else. The Earth is pulling you down. So yes, you are in contact with the surface, but we do call this a non-contact force because it is a field force. Jenny's going to talk a little bit more about that on the 1st in a couple days, so you can see it there too. I've seen that some of you say that there is just a little bit of a lag, and there might be for some of you, and probably what it is I'll write on something, and it might have a little bit of delay, but on my end, I'm running about 400 megabits per second, so it shouldn't be streaming issues at all. So it could be more likely on your end if your internet's just a little bit slow. All right, here we go. Let's go back through and talk about this. We did say that it is a physical quantity. It includes contact and non-contact forces, and it also measures and models. So it does those two things. And the College Board is really big on um, measuring and modeling. So actually giving numbers, and then also thinking about ways that you can present this information or try to explain to those of us who grade the AP Physics exam what this looks like to you. And so sometimes we call this a push or a pull, or I could say it is a 5 Newton push or a 10 Newton pull. So we could measure it, or we could just use models and kind of go through and do it that way. It is a vector. So remember, vectors have two things. They have magnitude and they have direction. And because they have both magnitude and direction, we know that the magnitude is measured as a number and it's measured in newtons. And direction would be similar to up, down, in, out, left, right, X, Y, Z, you name it. And you could give a direction in that way. You could also say it's this way or that way. So you can use hand signals. Really hard to do on an AP test, but you could do that, I guess, if you drew a little picture of somebody pointing in all these directions. Probably be a lot easier to just use regular X, Y, and Z. Okay, so that is really what a force is, but let's talk about the types of forces. There are several different types of forces that the College Board wants you to know. One of them is weight. Weight is the one that you will always have. And it should be one that you always start with. So whenever you draw a free body diagram, something that Peter Apps is going to actually talk about on Wednesday, when you do those, the first one I always have my students draw is the weight force, or the force due to gravity, which is mg. And I prefer that everybody uses mg or something similar to mg. Sometimes you'll have a couple of different objects. So you might have two objects like this, and they are connected by a string across a pulley system. And that pulley system is maybe attached to a table. And we call this an Atwood's machine. So it might be that I have M1 and M2. So when I would draw these, I would call these M1G and M2G. So just something really important to kind of think about. You could also write FG. You just want to be very careful not to write F capital G. That would not work. You would not get points for that. You could also write W, although the most common thing that you will see is MG. That's both in books and problems and the way that they'd like for you to do it on the AP test. The direction of this, you could say down, but you have to be careful because if you're standing on your head, down to you might be in outer space. So nonetheless, we always want to say this is toward the center of the Earth or of another planet or satellite. And by satellite, we don't mean like the Hubble Space Telescope, which is a satellite. We actually are talking about the moon, something that's large enough that it would be much, much, much larger than you are, and it would have a gravity that you would be able to experience. So remember, gravity is based on a couple of things. It's based on how far away you are from something, but it's also based on the mass of the two objects. So if even though I'm attracted to my wife, if I sit next to her, there's very little gravity between us. If I sit next to the Earth, which I'm doing currently, there's a tremendous amount of gravity. Not that love and gravity are the same thing, but that's kind of the difference between the two. So you have to be kind of careful. The normal force is a force that is always perpendicular to a surface. So if we think about maybe we have a table, and that table is horizontal like this, and I've got something sitting on that table, the force that would come up and be 90 degrees from that table pointing straight up or perpendicular would be the normal force. The other thing that you'll see on normal forces is they'll use inclined planes. They love to do this. So they'll have a ramp. And these ramps, if we put let's just say we put a box on here, and that box stays still, we know that that normal force points at a 90-degree angle to the surface. So you'll be really careful. Pointing straight down, which is not at 90 degrees, is going to be mg. So this would be n or fn, totally up to you. Tension is ft or t. You could use either one. I always prefer that my students use ft, And for this one, you could have it FN or N, but I like the FN and the FT because that differentiates it from period. So capital T also has the meaning of how long it takes for something to go around something else. For example, the Earth has a period of 365 days or 1 year going all the way around the sun. And so if you use FT, that makes it a lot easier for us to understand that that is the tension, and it is parallel to the rope. Now, what do I mean it's parallel to the rope? For example, if I have a bowling ball hanging in my room and there is a rope that is tied to that, then the tension force is actually pointing straight up from that ball. So it is pointing straight up, and that would be the force of tension. So we say that it's parallel to the rope. There's also two different types of friction. The first one is called sliding or kinetic friction. And this is of motion, but you have to be careful because it does not mean that it is rolling. So if I have something rolling, I make contact only at one point. So when this tire rolls over to the next position here, then that point right here now is down on the bottom, and it only touches the surface. It doesn't slide. So I like to call kinetic friction sliding friction. That makes it a lot easier to remember that it's sliding, and that's the movement. Static friction is when you have something that is stuck to the surface. There's enough friction there that it's hard to move. So you have to push. Once you start pushing a box, once the box let go, then you have broken the static friction, and as you slide the box, now you have kinetic friction. These are both parallel to the surface. So for example, this is our normal force, this is mg, and then my friction force, if it's just sitting on the hill, would be the force of static friction, and I would put it there. If it's moving or sliding down the hill, so if we said that it's got some sort of velocity in that direction, we would then change this to kinetic friction because it is sliding down the hill. The last one that we'll just cover briefly here is called the spring force. The spring force is also parallel to the spring. And basically all it is if I have a spring, so for example, in the Hooke's law apparatus, if you use it in a lab, you'll have a ring stand, and then next to it, you'll have a spring, and that spring will hang down like this. And the force of the spring, if I have a little ball down here at the bottom, the force of the spring will point upwards, parallel to the spring. So if we draw this a little bit bigger so that you can see it, so here's our spring. When that spring pulls on this ball, it is actually pulling straight up on the ball. So that is parallel to the spring's axis. And by the spring's axis, they mean if you look down the spring, so this is from a top view and you see all the coils going down, the axis would be pointing straight at you. So you're looking straight down into it. And those are the different types of forces. So far we're just kind of going through some things. The next thing we're going to do is we're going to have a little bit of an interactive activity. So that'll help speed things along a little bit. All forces have two things. We have an object, and the object is the thing that the force actually acts on. And the agent is the thing that's doing the pushing or the pulling. So we have to have something that is the receiver of the force, and we have to have something that is the giver of the force, essentially. And that's kind of a misnomer. We'll talk about that in a little while too. But here's what we're going to do. Let's do a little multiple choice. Hopefully you can see the bird. The bird is sitting motionless. Well, it's actually not motionless. It's bobbing up and down for a very long time. And it's on a perch and has two forces acting on it. I want you to, using the chat box, go ahead and go through, and I want you to tell me what are the two forces acting on the bird. So remember, Fg is the force due to gravity, Fn is the normal force, Ft is the force of tension, and Ff is the friction force. And I'm seeing a lot of answers, which is awesome. And those answers so far, I'll only see A and B. So far only A and B, and that, believe it or not, is the correct answer. So both A and B would be correct. So if we drew a free body diagram for this, which Peter Apps will go through on Wednesday and do, we know that straight down is the mass of the bird times gravity, and straight up, which would be equal and opposite, is going to be the normal force. So I could write mg, or I could make FG. So that is the answer. All right, cool. So let's go ahead and go to part 2 of this question. We still have the bird sitting motionless on the perch, and for each force there are 2 objects. Okay, so I have the perch and I have the bird, or I have the perch, or I have the perch in the earth, or I have the bird in the earth. So I want to know, for the force of gravity, so remember that's the one pointing straight down, what is the force acting on, and by what object does it come from? So remember, we're thinking about the bird. We want to know, what is the force acting on, and what does that force come from? So what is the by? So far, we've got several answers here. They all look like they're the same. You guys all have it. That is perfect. It is letter B. It is the bird. That is what is acting on. And then it is coming from the earth. So I have a question for you. Is this a C, contact force, or is it a NC, non-contact force? So let me know if it's a contact or a non-contact force. You guys are rocking this very good. So far, I see everybody is saying it is a non-contact force. Awesome. Let's go ahead and take a look at the next thing. So the next thing is for the normal force. So remember, that's the one pointing straight up. What is the force acting on? Okay, so remember, we're doing this diagram for the bird, and by what object does the force come from? So your answers here are bird perch, bird earth, perch bird, or perch earth. And I'm seeing a lot of answers here out of the corner of my eye, and it looks like 99% of those, ooh, very nice, Aaron, is A, which is the correct answer. So the force is acting on the bird, and it is coming from or by the perch. Excellent job. Let's go ahead and take a look at another one. So this is a really good one. Hopefully you'll like this. I'll give you a second to kind of digest that animated GIF that's going on in your mind here. They want to know what forces are acting on the player. What forces? Notice, because a lot of you have answered one of the forces, but I want you to actually think really quick. Yeah, here we go. Now we're doing better. So a lot of you had put D. And interestingly enough, that is one of the forces. It's got to be the force of friction. But there's also 2 more forces acting on this gentleman. And I'm seeing it now. And most of you are putting all those forces. So we really need to make sure that we have the force of gravity, the normal force, and the force of friction. Without these 2 forces, all that would be happening is you would just have the force of friction going in this direction. But you can't have the force of friction by itself. You actually have to have something that's interacting with our object. Well, the only way to have that is to have 2 things. We need to make sure that we have mg pointing down, and then we have to have the normal force pointing up. Which of these 2 are the most important when I'm solving for the force of friction? So remember the equation for the force of friction, and let's see if you can figure that out. Is it the normal force, or is it the gravity force? So you can either type you can either type N, or you can type W. Which one of these 2 is very important in order to have the friction force? And I'm seeing it. A lot of people have N for normal force, and that's correct, because remember, the force of friction is equal to, or kind of equal to, and then we're going to say mu N. We said that friction force is going to be less than or equal to mu N. Remember, that's because as you push on something lightly, if it doesn't move, and you push on it harder and it still doesn't move, your force of friction keeps getting bigger, but it's still less than mu N. As you finally get it big enough, then we can say that the force of friction is equal to mu N, but this would be kinetic friction. This one would be our static friction. So that's the difference between the 2. Awesome job. You guys are doing a great job. Here we go. Let's take a look at the next thing. It does say, for the force of gravity, what is the force acting on, and by what object does it come from? So your answers here are the player in the ground, the ground and the player and the earth and the player. This one, just like the last one, should be pretty easy to do. It is the player and the earth. It is not the player and the ground. The ground is not pulling the player down, okay? The ground is just sitting there, and that's holding him up. It's the player and the earth. Very good. Let's go ahead and take a look at the next one. For the normal force, what is the force acting on, and by what object does the force come from? So this is for the normal force. You want to be very careful with this one. Don't get on and by confused. And remember, the last one we just did, we had gravity. And so that came from the earth. So this one has got to be letter A, just like everybody has said. And that is on the player by the ground. So awesome job. That is definitely what is happening. All right, last question. So for the friction force, what is the force acting on, and by what object does the force, okay, come from? So we want to know for the friction force, what is the force acting on, and by what object does the force come from? And so let's just kind of see what we get here. So for the friction force, what is the force acting on, and by what object does it come from? And getting a lot of answers here. It looks like majority answers are letter A, and that would be correct. So remember, the friction force here is pointing in this direction, but that friction force is solely dependent on the normal force. So what do we mean by that? Well, here's what we mean. You always have mg. So when you're by the earth, you're going to have mg. But let's say that this player, instead of sliding, okay, has jumped. If this player has jumped and they are in the air and they are about to come down and do this little thing that's happening to his face right here, is there a normal force acting on the guy when he's in the air? So just give me a Y or an N. Is there a normal force when he is in the air? And you're correct. There is not. So is there a force of friction? So we're not talking about air friction here, and there's probably a little bit of that, but not enough to really worry about. Is there a force of friction when he's in the air? And the answer, you're correct, is no, there can't be, because he is not in contact with the ground. And because he is not in contact with the ground, there can't be one. Until he is in contact with the ground, he does not have a friction force. All he has is just mg. So he's flying through the air. There's probably a little bit of air resistance that is pointing in that direction. So we could put F air if we wanted to, which is also a type of friction, but we're actually going to have to call that F air. Awesome. Good job. Okay, so that one's a little bit more difficult. Now, this one is a skydiver. So you'll see the skydiver jump out of the airplane. And they want to know, what are the forces acting on the skydiver? So skydiver is jumping out of the airplane. What are the forces acting on the skydiver? And so far, I see a lot of people saying A or A and D. So if you're in an airplane and you're jumping out of an airplane, you have to wear some pretty nice protective goggles. Otherwise, the air will hit your eyes and vibrate your poor little eyeballs there. And you don't want that, because then you won't be able to see and you might get a little bit nauseous. So the correct answer for this one is both the force due to gravity and the force of friction. Some people are tempted, I think, sometimes to call it a normal force, but this one really is with a solid surface, okay? You can get into, well, if I try to stand on jello and I'm light enough, I can do that. Is that a normal force? Well, we'll go into that later. But right now, we're just going to say FG and then FF. But this one is really the force of air friction. So it's more of a fluid friction, I guess, is what we could say. But for what we're doing, we can just call it FF. So for the force of gravity, again, what is the force acting on? And by what object does it come from? So that's what we want to know. And it looks like you guys, we've done this one 3 times. So by now, hopefully you kind of know which one this is. And you were all correct. It is definitely letter A. It is definitely letter A. Thank you very much. That was easy. How about for the force of friction? They want to know, what is the force acting on, and by what object does the force come from? And I think a lot of you have this one also, just kind of looking at your responses. And that is correct. It is the skydiver and by the air. So it is on the skydiver by the air. So these are what we call action reaction, or we call them, if you remember, object interactions. So you always have to have two things, and only those two things will act on each other. But if you remember on the bird, we actually had three things. We had the earth, we had the perch, and we had the bird. But that's because one of them acted at a distance and the other one did not. Alrighty, so this is the last one. You'll like this one. So if you notice, this gentleman has a pug that he has fallen with. So a skydiver with an open parachute is falling to earth at a constant velocity. They want us to tell, what are the forces acting on the skydiver? Now, I gave you a hint because I circled our system, the system that we're really worried about. So you have to be very, very, very careful when you do this one, because you might be tempted to pick something that is not necessarily acting on the skydiver on this one. And I think we could probably argue about this one too, if you want to argue about it. This one, I would pick letter A for sure. So we all know that there's got to be some sort of gravity happening, because if not, then the skydiver would just basically float in there, and that would be really weird. There's no normal force, because the skydiver, even though right here, that person is on the ground after they land, here they are not. And this is the situation that we're looking at, this one right here. There is a tension force. Where does the tension force come from? So somebody put it out there. Let's see. Yes, that is correct. So Shania says ropes. So there are ropes, or there are parachute cords there, and that is directly connected to the person through a harness. So we know that. Some people, okay, I could see how you could pick friction if you wanted to. So I'll put kind of a flat face there. If you pick that, that's okay, but you have to explain why. Maybe there is air friction acting on this person, okay? But for what we're doing, we're just going to say that they are gently coming down. There's not a layer of air friction. There's enough that it kind of, we don't have to worry about it too much. It's really the tension in the ropes that is acting more equal and opposite than the force of gravity. So a lot of these, you could do a very good job of arguing that point if you wanted to, and we would give it to you if it was a free response. But I think for this one, though, what we're going to do is we're just going to pick A and C. Awesome. So for the force of tension, what is the force acting on, and by what object does it, and by it, we're talking about the force, come from? So what does that force come from? So this is skydiver earth, or skydiver parachute, parachute skydiver ropes, and ropes skydiver. So I'm seeing a lot of different answers. I am seeing skydiver and parachute, and I'm also seeing skydiver and ropes. So if you pick skydiver and parachute, realize that that parachute is up here and it is not in contact with our person. But it does not provide a force at a distance, or a non-contact force. It actually has a force with the ropes, and then the ropes are attached to the person skydiving. So the only interaction we're going to think about is the one in our circle here, which I can kind of put lines around. And so because of that, you have to pick letter E. And letter E is really the one that you want. Excellent job. Let's go ahead and take a look at the next one. So for the force of gravity, what is the force acting on, and by what object does it, and by it, we're talking about the force, come from? And you all have that one down now. So that is the fourth one we've done, and it is the skydiver, and it is the earth. So you guys are rocking this. That's very good. Alrighty, here we go. Next part. The next part. Newton came up with blank laws to describe motion. So what do we call that? Yes, I see a lot of you are typing. And oh, very good, Ella. Ella put 3, T-H-R-E-E. And that's ideally what we want. Some of you are just typing in the number, and that's also okay. So this one would be 3 laws. Does anybody know the names of the 3 laws? Here we go. The names of the 3 laws, this is very difficult, is Newton's first law, Newton's second law, and Newton's third law. Yeah, thank you. Somebody also said they are the Horner's laws. No, I did not discover them, thank goodness. Newton's first law. We can give this one a short name, though. It starts with an I. That is your guess. So anybody want to take a guess? First one to get it wins, and that is correct, Tommy. It is inertia. All right, cool. So the first law is inertia. Newton's second law is best represented by an equation. What is that equation? Anybody know? What is the equation? And I'm seeing a lot of people now typing the following equation. F is equal to ma. And that's kind of okay, but we need to do something better. So let's add this thing. What in the world does that mean? What in the world is that funny? Yeah, that is the summation sign. So the sum of the forces is equal to ma. Or you could say acceleration, and we really need to put a vector line over these. Acceleration is really equal to the net force, or the sum of the forces, all over the mass. So that's super important. Very good. Newton's third law. What would you say about this one? So the first one is inertia. The second one, we use an equation. And if you had to give some sort of short phrase to explain, very good. So I see equal and opposite is what somebody wrote. Thank you very much, Max. So opposite, equal, and opposite, that is perfect. So Newton's third law, that means that we have a force that is being shared by 2 things, and it is equal and opposite. So it could be the normal force, could be force due to gravity, could be tension force, friction force, any of those. Very good. All righty, here we go. So Newton's first law, the poor definition of this, the one that is terrible, the one that you really should never say, is the following. An object in motion stays in motion, and an object at rest stays at rest unless acted on by an outside force. Why in the world is this a bad definition? Well, let's use some cheerleaders to figure this out. So these are cheerleaders from Hudson Athletics. I think it's a college team. And anyway, we have this young lady in the middle. What is the force that is coming down this arm and going down this arm? So what are those 2 forces? If you had to say that she is the dot, okay, and we have 2 forces, one going each way, what are those? Yes, those are the forces of tension. Very good. So those are the forces of tension. We also, it looks like we have a force down here, and that is pushing up on her. So I'm going to start at her and show up. What is the force up? Okay, cool. So I do see some of you saying it's applied force. You could call it that, but typically we won't say F-ap because the tension would be an applied force also. Instead, a lot of you are writing Fn, and it's because there's a 90-degree force with people's hands down on the bottom. There's also one more force. The last force is mg pointing down. I have a question about Fn and mg. Are those 2 forces equal and opposite, or are they unequal and opposite? What do you think? Equal or not equal? So you can either type E or N. Yeah, those have to be equal. If they weren't equal, she would be moving up or down, correct? Or accelerating up or down, I guess. How about the 2 forces of tension? Let's call this one number 1, and let's call this one number 2. Are those 2 forces of tension, Ft1 and Ft2, are they equal or are they not equal? I see yes, and I see lots of E's. They are equal. Good. So if we're saying that, it says she's at rest right now, correct? But there's an outside force. In fact, there's 1, 2, 3, 4 outside forces. But she's still at rest. Do you see why this is a bad definition? Would you like to know the correct definition for this? And your answer would be yes. Very good. All righty, here we go. A much better definition. If there is no net force on an object, then the object remains stationary or it moves with a constant velocity. So is there a net force on our young lady? What would the sum of the forces be on our young lady, or the net force, what would it be if she is just here and she's not accelerating it? And I see everybody's writing it. It is 0. So this is what we call balanced system. And the first law, this is the better definition, if there's no net force on an object. So we really have to be careful. And I think that's something a lot of teachers, including me, don't do very well in class, is define these better. So that's a much better definition. Here we go. Let's do the next law. Newton's second law. So this is me lifting weights. Not really, because I don't think I could pick one of those up with 2 hands, let alone 1. So the poor definition is force equals mass times acceleration. My question is, what's wrong with this? What is wrong with this? Yeah, very good. So somebody just said which force, because I know that there is a force from the weights. So I'm going to put MW for the weights pointing down. So MWG, and it's a little bit in his arm too, but mainly the weights. What is the force pushing up? So what would we call that? This would be F. Yeah, Fn. You could call it Fap, but let's call it Fn since it's a contact force and we are on a surface and it's a 90 degree. If it wasn't at 90 degrees, that could be really bad for this person because it would either fly out or fly in and crush his chest. We don't want that. So the question is, what's wrong with this? Well, it says force equals mass times acceleration. But if this person is just holding this and there's 2 forces, it's not accelerating. It's not going in. It's not accelerating. And because it's not, we need to change this definition. So let's change this definition. I see another question, which is awesome. I'm going to check that question really quick just to see. Yeah, so somebody just asked, should anything that is thought of as FAP really be FN? It could be. If you think about, and I know this is kind of a sidelight, but it's okay, we've got some time. This is a really poor diagram of an airplane, but I'm doing the best I can on the fly. And here's an engine underneath. That engine is pushing the plane this way. So you could call that an applied force, but we also like to call this the force of thrust. Okay. This person is pushing up, so you could call it the force of the push or the applied force, but it's really a normal force. So I think we really want to think about what is the interaction here. This one is the force of thrust. It is that. Yeah, I like it. So on the fly. Ha, get it? That was a good pun. So let's go back to the question at hand since I got a little bit distracted there by the question, but it is a very good question, Mr. Aaron. Thank you very much. What was wrong with this? We said it is not accelerating. Okay, so what is not accelerating? Well, it is accelerating up and accelerating down at the same time. Let's do a better job of doing a definition here. The better definition is an object's acceleration is the result of the net force on the object divided by the object's mass. So here we've got a truck. It looks like it's going to pull this big tree, and it really just has a little tiny tree in a container next to it. That's kind of a funny little thing going on. So the question is that little tree accelerating? Absolutely it is. So why is it accelerating? Because the sum of the forces, or the net force acting on that tree, is accelerating it to the right. So the acceleration is to the right. So remember, acceleration is also a vector. This one, there is no acceleration, but it's not because there's no force. There are 2 forces. For Aaron, it would be the normal force or the applied force. And we also have the mg, or the force due to gravity. And those 2 are equal and opposite. So our net acceleration is 0. Okay. Hopefully that helps. That's a really, really, really important point. I think both Newton's first law and second law, we have all learned them wrong. And until you kind of go through a class like this where you really have to understand the true difference, it's the net force. So if you always remember net force, your first and second law will always be right. And that should be helpful. All right, here we go. Third law. I'm sorry, this is just evil. This poor little kid here. She gets tossed. So here's the question. For every action, there's an equal but opposite reaction. But if I pull a child in the wagon moves forward. That's not equal and opposite, is it? So think about that. Think about it. If I make this the wagon, and I am pulling on the wagon. So the kid's pulling on the wagon. We could say that's the force of tension, maybe, if you want to. I guess you could do that. You could also call it a normal force between the kid's hand and the inside of the handle. But then going the other direction, what is that? So going in the other direction, if he's pulling this way, maybe there's some sort of force of friction going the other way, because we know that it's on grass. The heavier the little girl is, and by the way, she's fine. She got in and pulled him around and tossed him over too. But there's a force of tension that the kid's pulling it with and a force of friction going the other direction. And those are equal and opposite as long as it's moving at a constant velocity. But if I pull a child in the wagon, that doesn't sound like it is, does it? Well, we need to change our definition. Here's our definition. If A exerts a force on B, then B exerts a force on A that is equal in strength and opposite in direction. So really what we need to do is just think about the handle. If I pull on the handle, so if this force of tension, okay, on the handle is coming from the boy, then there is also, there's also the force, okay, that is some sort of resistance that is on the boy from the handle. It's also a tension force. So we're just thinking about here, there's a tension force going this way and a tension force going this way. Somebody just brought up the fact that you could think about a wall, and if you're standing and you push on the wall, when you push on the wall, there is a force, a normal force that is pointing towards you, and that is the normal force on your hand from the wall. And then there is a force on the wall. So there's a force on the wall that is the normal force on the wall from your hand. And those are equal and opposite. So the big question that everybody asks is, why in the world does this wagon move? Well, because there is another tension down here that is pulling on the wagon, but there's not much of a force of friction here. So the force of friction here is going to be very small compared to the tension. So we'll even draw this tension a little bit bigger. So there's a force of tension pulling in this direction. So now we have a net force. And because we have a net force, we have the total mass of the girl in the wagon times the acceleration. And that is a better definition. So be very careful. If A exerts a force on B, then B exerts a force on A that is equal in strength and opposite in direction. The only way that she moves is if this tension force is bigger than the force of friction. In fact, all the movement comes from the interaction of the boy's feet with the ground. If he was on ice, the whole system would go nowhere. And that's the really important part. So hopefully that's helpful. All right, so let's do some practice. We've got about 10 minutes or so left, and we're going to spend about 3 or 4 minutes on each one of these questions. I'd like you to take your time, think while you do these. These are actual, very, very close to actual AP questions. And the first one is Apollo 13 is a 1995 movie about the mission to the moon that experiences serious problems. In the movie, an astronaut says, well, we just put Sir Isaac Newton in the driver's seat. This line, a reference to Newton's first law. So remember Newton's first law. Tell me if I say it wrong or if I say it right. Things that are moving will continue to move. Things that are at rest will stay at rest unless a net force acts on them. Remember, that is the right way to say it. So be very careful. Yeah, very good. That is the right way to say it. Is spoken just after, and then here are your choices. The rocket begins firing its engines and lifts off from the launch pad. The spacecraft begins firing its engines on its way back to Earth from the moon. The spacecraft enters the Earth's atmosphere and air resistance begins to slow it. Or the spacecraft has finished firing its engines and has spent all of its fuel. Which one of these would be the correct answer? And take your time with this. Make sure that you're thinking about it before you do it. I've seen a lot of the same answers, which is awesome. Very good. So this one is letter D. So why is it letter D? I guess that's the question. The reason it's letter D, and in fact, let's go ahead and move it to letter D here. The spacecraft is finished. Remember, the spacecraft has finished. Um, the spacecraft has finished firing its engines, and when it's not firing its engines, there is no more net force acting on it. So the net sum of the forces here is equal to 0. So it's going to just travel at a constant speed. That's why we're referring to inertia. Yes, couple of questions that people have said. One of them is, will air resistance always be included, or will it be clearly written out if it is involved? It will be clearly written out. It will be clearly written out. It will say ignore air resistance. Otherwise, you include it, especially if you're talking about jumping out of a helicopter and then you're in a wingsuit and you go down and then a parachute comes out. Is there anything that is thought of as F app that really should be okay? So we answered that one already. Oh yeah, so somebody else asked if every action was equal and opposite, how do we have acceleration? And it's because there's friction between your feet and the ground. So if I am trying to pull Joe, the only way I can accelerate Joe is if I am touching the ground. And there's another action reaction force there. And that action reaction force has to be bigger than the action reaction force of me pulling. So if anybody has any questions, then I will, in class tomorrow, if you're on here and you're in my classes, I will show you why that happens. So Joe, I will do that for you tomorrow. And no, it is not that, Alex W. Aaron Wapple, I will also show you tomorrow, and I'll introduce you to who Joe is. All right, cool. So just making sure we answer the questions as we go. I have not forgotten about the tug of war question that we will tackle here too. All right, very good so far. Let's go to the next one. We have an aircraft flying to the right, has a constant horizontal speed, constant horizontal speed, constant horizontal speed. Is it accelerating? Yes or no? Is it accelerating? Very good. Not accelerating. Why? Because it has a constant horizontal speed. It also has 4 forces. When the aircraft passes through the cloud at point S, the force of thrust has the same magnitude as the force of drag, and the force of lift balances out the force of weight. If the condition continues, which path will the plane follow? And so here we go. Let's see which path the plane is going to follow. And for those of you that have a little bit of a delay, that's why I give you a lot of time to try to answer these, because I know some of you are seeing the chat come up, but you're still listening to me talk. So I get that. Yes, because the forces are balanced, it should fly along letter D. And that is a perfect answer. Excellent job. So far we are 2 for 2 for some awesome answers. You guys are doing great. It is letter D. Okay, this one's a little bit more difficult, but let's see how we do. It says a skydiver falling through the air opens her parachute. The skydiver and parachute together have a weight equal to mg. So that's our weight. At a specific instant after the parachute opens, the force of air resistance on the parachute is 1.4 mg. They want to know what is the acceleration on the parachute and skydiver system at this instant. When you answer this one, I would draw a free body diagram. And remember, mg cannot change unless something dramatic happens. For example, if you have a car, the car falls apart, or you have an airplane and it's falling and the wings fall off, or you're falling and I don't know, maybe you're wearing a parachute and it falls off. I don't know. So they want to know what is the acceleration on the parachute and skydiver system at this instant. Yeah, I'm seeing a lot of really good answers here. And I'm seeing more of the right answer than I am the wrong answer. So remember mg, if mg is going to be 1, okay, so we have a weight of mg, then the force of air resistance is 1.4 mg, then our acceleration would have to be 4 meters per second upwards, 4 meters per second upwards, okay? So if we divide by m, okay, so if we take this and we get rid of that m, we would have then 4 meters per second squared upward. That would be our acceleration. Very good job. Nice, very nice. Essentially, this one is 1.4 mg, and this one is just 1 mg. So our acceleration is going to be 4 times 10, which is 0.4 times 10, which is 4. Excellent job. All righty, here we go. A car travels. We just got a couple more of these. A car travels up at a constant speed. Which of the following diagrams best represents the forces acting on the car at this instant? Notice that the car is traveling up the hill at a constant speed. Which of the diagrams best represents the forces acting on the car at this instant? And Matthew, you are 100% correct. That last one, it is because of that. This is one that probably 90-some% of people got wrong on the AP test. So this is a trick question. All right, you guys are doing a great job. Everybody has answered the same thing. You've answered B, but B is not the correct answer. Here's why. Let's do this. Remember, there's a fun little thing that we do with these. We draw these components because we want the forces that are going in the direction of motion. So we really want to think about the forces in the positive parallel direction. Remember, that's positive parallel, and this is positive perpendicular. So if this is my friction force going in this direction, and this is W, and let's put an angle here. This is W times the sine of the angle. And this is equal to this. And the only reason I know they're equal is it's going up a hill at a constant speed. This is the force that's trying to pull him down. So Aaron, your A with the question mark is correct. So we can get rid of the question mark. Here's why this one is A. It's because there is not a force listed here, because you have to remember that components have to be considered when we look at this. Here is W times the cosine of the angle. That one is equal and opposite the normal force, so the car doesn't lift up and doesn't fall down into the hill. And then we have the force of friction going in this direction, and we have W sine of the angle pulling it down the hill. So that's why. Does that make more sense to those of you who are looking at this going, oh my goodness, what is he doing? Nope. Think about it. That's what you're going to have to do. You're going to have to think about this one. Remember, forces have to be balanced in each direction. So up the hill, down the hill, balanced, up and down. So from the hill up and from the hill down have to also be balanced. All right, that one's a hard one. That one's why a lot of people miss it. This one's a lot easier. 3 forces of equal magnitude act on the box shown. 1 force is up, 1 force is down, and 1 force is to the right. That would be your right, I guess. Or maybe this is your right. One of the two. Which of the following statements must be true based on this information? Select 2 answers. Select 2 answers. Ooh, somebody asked about the force of friction on the last one. We'll look at it too. All right, here we go. I'm seeing a lot of answers here. All right, so I'm seeing A and C, and I'm also seeing C and D. I'm seeing C and D primarily. And the actual answer here is C and D. We know the velocity is changing. We know the acceleration is directed to the right. This box could be moving to the right and accelerating. So if this is positive velocity and this is positive acceleration, we would say it is speeding up. But if it was moving to the left and had negative velocity, what would it be doing? Yes, a lot of you are typing this, SD, slowing down. That's perfect. It would be slowing down. Okay, very good job. So that's why you can't pick A. It doesn't have to have a rightward component of velocity. So it does not need to be moving to the right at all. It could be moving to the left. So it'd be like if you're in your car and here's your car, here's your windshield, okay? You're in the car. If you're moving in this direction, there doesn't need to be a force in that direction. Okay, there's probably, if the net force is back this way, you're probably hitting your brakes. And that's why, remember, this is net force, okay, for this diagram. Alrighty, so that's why that one is the way it is. We had one person that wanted to know one more thing. And that one last thing, whoops, is, so hold on, I'm going to get rid of this really quick. They wanted to know why, and we'll open this guy up one more time. Oh, why couldn't it have been B? Somebody wants to know that, so let's have a look at it. The box has no vertical component of velocity. Actually, it could. Just because these are balanced doesn't mean it can't be moving in that direction. So, for example, let's say that I am in a balloon. Okay, so I'm in a hot air balloon. Can the hot air balloon be moving up at a constant velocity? Yes. So if it's moving up at a constant velocity and there is no acceleration, then these two forces are equal and opposite. So that's why. Does that? Yeah. Oh, good. That's what I want. All right. So the last question that somebody had was, it actually was the very first question. The very first question was, explain Newton's third law in terms of a tug of war. So if team A, so here's team A, here's team B, and here's the center of the rope. Team A is pulling, whoops, sorry, I already put an A. Team A is pulling with 100 newtons. So we have a force of tension in this direction, 100 newtons, and we have a force of tension in this direction with 100 newtons. And you can't see a thing I'm doing. And you are absolutely right. So let's get it so you can see it. How's that sound? So we're going to close that. Hi guys, sorry. So let's go back so you can see this. Share. And now you can see it. I'm really sorry about that. All right, here we go. So we've got team A pulling in one direction, team B pulling in the other direction. So there is a force of tension going in each direction. This thing, is it accelerating, is the question. And your answer is no. So some of the forces here have to be equal to 0. And we're going to call this Ft1. We're going to call this Ft2. So Ft1 minus Ft2 has to be equal to 0. So that means that Ft1 is equal to Ft2. And we've already said that. We said that they're both 100 newtons. So if you're doing a tug of war, let's say that this is 500 and the middle of the rope is not moving. Okay, so we're going to say Ft1. We don't know what it is. We know Ft2 is 500, and that's equal to 0. If it's not accelerating, then Ft1 also has to equal 500 newtons. So that's why when they say explain Newton's third law in terms of a tug of war, this is why. There is no acceleration. Now, if you were doing a tug of war and one team let go and the other one pulled, then you still are going to have equal and opposite forces. It's just that this team is going to be pulling, and they'll just be pulling the weight of the rope, and the weight of the rope will then be the same regardless, okay? And it's actually the people are moving and they are pulling harder on the rope than the rope can pull back. And that's why it doesn't go anywhere. So that is the important part. Alrighty, we are out of time. I think we've answered all the questions, hopefully, that you all had. And so that one is it. Alrighty, cool. So thank you so much for everybody that showed up. If you were one of my students, I have you recorded down here. And you are good, and I will see my students tomorrow. And if you are not one of my students, thank you so much for coming to this. Hopefully it was super helpful, and it probably, hopefully, cleared up some misconceptions, and it will help you as you continue to progress in your study of physics and forces. Talk to you later. Thank you, guys. Bye-bye.